Okay, so everyone, welcome back to the Tutte Colloquia after 2 weeks of break due to rescheduling issues. So today we are happy to have John Yacht. He graduated from Stanford and joined Waterloo IQC in 2016. He's going to talk about algebraic formulations of Zauner's conjecture. So take it away, John.
All right, thanks, Jane. Okay, much better. So thank you everybody for coming, and sorry for the rescheduling some month or two ago. I guess there was an overlap with everybody was busy doing. So thanks everybody for coming in the middle of summer. So today I will talk about Zauner's conjecture, which you might have heard of in many different guises, such as, how many complex equiangular lines can you have in a given dimension? What's the minimal size of a complex projective 2 design? Maybe you've heard of equiangular tight frames, and there's a whole bunch of easy bounds to prove that are hard to prove that they're achieved, but they're apparently all achieved by like the same common structure. So I say apparently because there's a lot we can't prove yet. And throughout this talk, I tried to put things in red that are things that we know are true, but have not yet been proved. So maybe to just start with something simple. So suppose I've got some list of vectors. I've got n vectors in d complex dimensions, and they're such that if I have the standard Hermitian inner product between any two different vectors, it's some constant alpha, the absolute value squared. So it's a real number. And suppose that they're just for this argument that they're normalized to length 1. And so it's very easy to prove that you can have at most d squared such vectors in d dimensions. And here's how you prove it. What you do is you make rank 1 projections out of these vectors, and then each of these projection matrices is now, you can think of it as a vector in d squared dimensions. And if you then consider the gram matrix of these projection matrices according to this trace inner product, so like trace pi pj is like an inner product between operators, that you just get some big d squared or n by n matrix with 1s on the diagonal because they're normalized, and alphas, this common overlap off the diagonal. And if you just take the determinant of that, you get this quantity here. And let's see, you can see that that's always non-negative if the vectors are distinct, okay, which we assume they are. And so that means that this set of n vectors that we've written down with common overlap must be, or I should say the matrices, the projection matrices must be linearly independent in the space of all matrices, because this gram matrix determinant is non-zero. So that means that we can have at most d squared, which is the real dimension of the space of d by d Hermitian matrices. So you can have at most d squared such vectors. Okay, so this is like one simple instance of a more general type of bound known in combinatorics as linear programming bounds. Very easy to prove. I did it right here, but it's also not too hard to show that if this bound is achieved, then that common overlap has to be 1 over d plus 1. But maybe the surprising conjecture due to Zauner, maybe 20 plus years by now, maybe 23 years ago, that this bound is apparently achieved for all d. And that's kind of what this talk will be about, is why do we believe with increasing, why do we have an increasing belief that this is true, and why do we keep being unable to prove it? So just for comparison, you consider the case over the real numbers. There's an analogous bound where now you're looking at the real dimension of the space of real symmetric matrices. And that's just d squared plus d over 2. And this bound is rarely tight, it turns out. So and actually, if it is tight, it's been shown that basically the dimension has to have or that this overlap has to have a certain form like this. And if we kind of just look at what's known about the maximal number of real equiangular lines in dimension d, I've written kind of what's known here, some of what's known here. You see that like in dimension 2, there's exactly 3, which is not too hard to think about. You can just picture it like the 3 lines going through the opposite corners of this hexagon. Okay, so there's 3. There's going to be 6 in dimension 3, and that matches this bound also. It's the lines going through the opposite vertices of this 3D here, I think the icosahedron. But then there's still only 6 in dimension 4, whereas that bound gives you 10, and you keep going up. The next time it's tight is dimension 7. I mentioned that the fact that the max is 28 in dimension 14 was only just proved like a few months ago. I should have a reference here, but I don't. And then going, you go further, it turns out in dimension 23, there's exactly 276. And that's the max all the way up to 41 and et cetera. This has to do with the Leech lattice, whereas this construction here comes from the E8, the E7. It's the 56 dimensional representation of E7. But I'll just mention, so there's a lot of, so things aren't so tight here, they're not so nice, but I will say that one thing that is very nice is that there's a very clean way to understand all these, like all the constructions, because they correspond one-to-one with strongly regular graphs, and they give you explicit constructions via that matter. But like looking for examples in higher and higher dimensions means you're looking for bigger and bigger strongly regular graphs, and that's why we don't know as much as we'd like to. But so in quantum information theory, there is this notion of what people call a SIC-POVM, and actually this problem kind of, at least nowadays, SIC-POVM or SICs is kind of the language attached to this problem. It turns out that maximal sets of d-squared equiangular lines give you SIC-POVMs. So what is this? So a POVM is basically a bunch of matrices that sum up to the identity. They're positive semi-definite matrices that sum up to the identity matrix. And they model a quantum measurement. Okay, the idea is that you can perform some measurement and you can compute the probabilities of the outcomes of measurements based on just kind of a representation of your state as a positive operator and this collection of sort of measurement operators. And so a SIC-POVM is going to be a bunch of rank 1 projections, or really they're kind of, you have to rescale them. But the upshot is that they're symmetric and that they have this same kind of overlap, similar to before. And they're informationally complete, meaning that they span the space of Hermitian matrices. And one thing that's nice about SIC-POVMs is that if you have the measurement statistics, it's very easy to reconstruct the state. And I won't say more about that, but I can if you're interested. So there's a closely related notion of a 2 design, which is in some sense, it's kind of like the opposite of a set of equiangular lines. In the sense that equiangular lines, there's some upper bound on the number that you can have in a given dimension. What a design is it's something that lets you kind of simulate averaging over like a continuous space just by averaging functions over some discrete or hopefully even finite subset. So now, like intuitively, you might expect we need to have enough points to simulate a nice distribution. So you're going to want some lower bound. And it turns out that that's what happens here. But just maybe to give a concrete definition, I'll say more about this in the abstract later in the talk. But I'll say a set of rank 1 projections, P1 through Pn, I'll just define these to form a complex projective 2 design. If I take the average of these things, they're the tensor powers with themselves. So this now is so if these are like, D by D matrices, this will be some D squared by D squared matrix. If this thing is proportional to the projector onto the symmetric subspace, that's the subspace of all vectors that are fixed by swapping the 2 tensor factors. So, like the span of like psi tensor psi, that kind of thing. And so this is just some nice operator who's actually dimension winds up being exactly 1 over this, okay? So another easy theorem says that any 2 design, any complex projective 2 design in D dimensions, it's going to require at least D squared points. Okay, before we had at most D squared, now we've got at least D squared. And if this bound is achieved, well, then they have to be equiangular. So they will end up being an instance of what I described on the first slide. Okay, so these SIC-POVMs that I mentioned before, they're also minimal complex projective 2 designs. And I'll just kind of mention that this certainly can generalize to higher T. And I'll say, well, you just kind of take more tensor powers here, and then it's the Tth symmetric subspace. And there's, so, the stuff I'm mentioning about complex projective space, you've also got real projective space, which is the notion of real equiangular lines. You can also kind of work with just a sphere instead of the projective space, or quaternionic or even the octonionic projective plane. And there's analogous statements for these 2 designs holding. And maybe I'll just say one more thing, which is that like, whenever you achieve this bound, we call it a tight 2 design. And tightness is like a sufficient condition for minimality. And so people talk about tight T designs, and I think that's why I kind of wrote this here in that context. But okay, so there's lots of equivalent formulations of this problem. So some of which I mentioned, some of which I haven't. So maximal sets of equiangular lines, and instead of looking at lines, you can think of the complex projective space as some curved manifold with some metric on it, where you measure distance according to like the shortest geodesic, measured by, in this case, by what's called the Fubini study metric. So it turns out that it gives you the same thing, basically, that the geodesic distance corresponds to the overlap in some very straightforward way. These also are called tight frames. Essentially, these rank 1 POVMs are examples of tight frames, where the word tight here corresponds to, in the design sense, for like 1 designs. The minimal 2 designs, as I mentioned. These are also regular simplices kind of inscribed into the convex set of density matrices. You've also, there's sort of another way to easily show that these configurations define certain isometric embeddings of L2 and D dimensions into L4 and D squared dimensions. And people often in computer science to study like approximate embeddings of this form using like Dvoretsky type theorems. And this is an exact embedding. And also numerically with an undergraduate student, Michael Pang, many years ago, we investigated numerically this conjecture that these also correspond to maximal volume simplices embedded in the convex set of density matrices. But I put that in red because I haven't proven that. It's the same as the others yet. And of course, these SIC-POVMs. So any questions so far before I jump into examples? Okay, so I think the simplest kind of non-trivial example is dimension 2. And here, the complex projective line is topologically just a sphere. It's a 2-dimensional sphere. And if you just imagine inscribing a cube into the sphere like this, and if you just take the opposite corners that form a tetrahedron, that gives you an example of a SIC-POVM or a tight 2 design. Or I'm going to use these different words throughout the talk, but I'll probably fall into calling them SIC-POVMs. So yeah, so you could just imagine inscribing this 4-dimensional or this 4-sided die in here, and those four points are the 4 different rank 1 projections of the POVM, and all 8 corners have a form like this, where X, Y, and Z are these special matrices known to physicists as the Pauli matrices. And what's especially neat about this is that I can just take kind of one corner, and if I act with these matrices, well, let's say by conjugation on the projector, or just by acting on a single vector and ignoring phases, I get 4, I get 4 different vectors. So I take one and I take that orbit under this group and I get the other 3. Okay. And so that group, it's the Pauli group is essentially abelian, meaning that like if I mod out by the center, it's abelian. It's Z2 cross Z2. Okay. And one thing I will mention is that you can kind of picture in your mind, there's an order 3 rotation that fixes any corner, really any pair of opposite corners, right? It just takes the faces around, permutes them. And it turns out that basically if you take the group of all symmetries of the cube, this is something people call the octahedral group. It has 24 elements. And actually you can realize it as a semi-direct product of Z2 cross Z2 with the finite group SL2 over Z2. So this is a group that's just over the finite field F2. It has 6 elements. And it's sort of like a discrete analog of the harmonic oscillator setup that shows up in quantum optics, if anybody's seen that before, or in Fourier analysis. So yeah, so there's kind of this, to summarize kind of Arning dimension 2, there's this kind of like striking structure here, which is that we can just look for a single point and we have this group orbit. So we just consider the group orbits of different points, and it's only these 8 corners under the specific group orbit that have an equiangular orbit. And there's also this nice symmetry group of this cube. And if you take the whole symmetry group, there's some order 3 subgroup that fixes each corner. And in this case, they wound up being exactly the fixed points of that order 3 symmetry. And maybe to spoil part of a punchline, the reason I'm emphasizing that so much is that this kind of structure shockingly seems to generalize. So going into D dimensions, I can write down some matrices that generalize the Pauli matrices, which people creatively call the generalized Pauli group sometimes. It's also known as a finite Heisenberg group. And so the upshot is I have these matrices X and Z. Later in the talk, I may call them X sub D and Z sub D, but not on this slide, apparently. And the idea is if I take these matrices, they define some group, and let me take the group generated by them and all scalar matrices. So this U1, I mean just like all like complex phases of norm 1 times the identity matrix. Okay, that's just to make our lives a little simpler. So this is a group. It's non-abelian, but it's, you know, it has an abelian quotient by the center. So that's what this sequence here. It's an exact sequence. It means that like the image of one is a kernel of the next, or it's another way of just writing, you know, it's a fancy way of writing this group mod this normal subgroup equals this group. Okay, that's, if you can just take that as a definition of when these things show up in the talk. And so what this X is, it's a cyclic shift. It's cyclically permuting the vectors, you know, 0 through D minus 1, you know, we're labeling them mod D. And this Z here is doing kind of a similar thing, but it's putting a complex phase on each basis vector, where this zeta D is not on the slide, but it's e to the 2 pi I over D. It's a D-th primitive root of unity. And the idea is that if I say fixing a section, what I mean is just choosing an arbitrary element up here to represent a given element on this kind of finite plane. So just pick your favorite ones. Like if you like, just, I could just ignore this phase and just call it xj, zj, xj1, zj2. These phases are a little nicer for certain reasons. So if you pick this section, it satisfies some nice properties, like the dagger is the minus. I think for this, you have to calculate mod 2D always. Oh, and then you have this nice kind of group property here, which shows you that they form a projective representation. Okay, so if there was no phases here, it would be an ordinary representation, but this is projective. So there's some kind of, it's a little more non-trivial. So a definition, I'll call some vector in D dimensions a fiducial vector if its orbit under this projective representation gives you a SIC-POVM, or is equiangular, blah, blah, blah. Right? So up to phase, there's D squared just matrices. And the nice thing is that this makes our lives a little easier, well, assuming that they exist as such orbits, but they do. So then you only have to look for one vector, not D squared vectors. Okay, so what people have now started to call, or some people have started to call, Zauner's weak conjectures that, well, these SIC-POVMs exist for every D, like I put earlier in the talk. But his strong conjecture says that these fiducial vectors exist in every CD. So in other words, that for every dimension that there exists a SIC-POVM that's in orbit of a Heisenberg group, finite Heisenberg group. And actually, it turns out that there's literally only one known SIC-POVM that is not in orbit of this kind of a finite Heisenberg group. And this is something that was found by Hager back in, I think, '83. He has this nice paper with a great title called 64 lines from a quaternionic polytope. But basically, Zauner finds a dimension 8 SIC-POVM from 3 copies of the Pauli group. So it's like Z2 to the 6 instead of Z8 squared. But apart from that, every other one anybody's found is kind of unitarily equivalent to one of this form. And I think Zhu has, for example, proven that in prime dimensions, they're always going to be Heisenberg orbits. So these kind of things are people prove. Okay, so in dimension 3, all the fiducials either look like this or they're on an orbit of one that looks like this. So I should say they're either, it's either coming from a Heisenberg orbit of a vector like this, where you kind of have, just the same weight on 2 different of the basis vectors. Or, there's a certain symmetry group I'll get to that you can always use to put it in this form. And so, this is basically the only case we know of where there's infinitely many, or an uncountable infinity of fiducial vectors in a given dimension. But I put this in red because I can't prove that I can't yet prove that this is the only case where there's infinitely many. But I don't think that's terribly hard to prove. In dimension 7, I just really love this example because it had really initially been found much earlier in papers by Appleby and Scott and Grossel, where, but I managed to kind of further massage and kind of isolate a really nice one in that dimension that I can just write down in a clean way in a talk like this. And so just to explain what's happening here. So there's 7 basis vectors, J going from 0 to 6. If this is a basis vector, we call this a ket in quantum mechanics. Hopefully everybody's seen this at least some time by now. This is the Legendre symbol. It tells you whether or not J is a square mod 7, and it's 0 when J is 0. And so defined like that. And basically I just mean this to the plus or minus 1. So it's either you take this or the inverse. And it turns out that I can expand that also as a vector like this, where x1 is just the vector of all ones, and x minus 1 is just encoding this Legendre symbol. And so I'll mention that there's a similar example in dimension 19, but there's sufficient evidence that this doesn't generalize. Actually, I should have put that in red too. I haven't proven that, but I know it doesn't, and I'm not bothering looking for more. The upshot is that there's a ton of symmetries that sort of show up accidentally in some of these simpler cases, and a lot of symmetry makes this one look nicer, and similar thing happens in dimension 19. But the thing that should frighten anybody that knows some amount of number theory is that the relevant number field, well, maybe this shouldn't frighten you yet, but I'll say the relevant number field has a non-abelian Galois group. And I'll tell you more about what this means a bit later. But what should be frightening is that it's a non-abelian extension of a real quadratic. And I'll say probably too much about that a little later. But to move on, okay, so we have explicit constructions, meaning that there are computer assisted proofs of existence in a growing number of dimensions. And it's certainly probably more than what I've written in this slide already. But here's a list of dimensions going up. I believe this is the largest record I've heard due to some computations that are ongoing by Ingmar Bengtsson and Marcus Grossel. I'll say more about kind of why these giant numbers are popping out. But I mean, many people have contributed, coming all the way back to kind of an early computer study by Scott and Grossel, which I will show you more about later in the talk, and others. Okay, so numerical, like inexact solutions are really not hard to do. Like if you were bored, you could probably code up and you knew some programming, you could start coding up, looking for these things by the time I was done with this talk, if you're good at doing numerical computations. It's just some degree 4 polynomial in many variables that you can just ask Python to minimize, and you get something that's close to 0, and it's probably a solution. But close to 0 isn't 0 necessarily. But if you're working over numbers that give you an exact representation, so-called algebraic numbers, these are like roots of polynomials with rational coefficients, then if you get something that's 0, or if you get that the difference between all the overlaps is exactly 0, then you know that you truly have something that's equiangular. And so that's why we're able to say that with certainty that they exist in these dimensions. But I will say that the apparent structure of the constructions lets me say with certainty that it's always true. And I'll tell you why that is the case later. But yeah, so they're algebraic numbers. Okay, so some polynomial, but what polynomial? What algebraic numbers? So in this paper by Marcus Appleby, Steve Flamia, Gary McConnell, and myself, which was published maybe last year in Acta Arithmetica, an old number theory journal, we put forth a conjecture that these number fields have a very specific form, namely that they're controlled by arithmetic in a certain real quadratic number field. Okay, so that's where I take some integer d, actually this specific integer d, take the square root, and you take all polynomials with that with rational coefficients. So it's some two-dimensional rational vector space of numbers, if you will. Just to give you an example of the flavor of the kind of things that we can show, though the implications are a lot deeper than what I have here. So let's say that you want to know the list of all dimensions in which the relevant number field is an extension of Q root 5, which is actually like the I guess it's like the minimal discriminant of all quadratic fields, at least real quadratics. And so then it turns out that all those dimensions have such a form like this. So I take the golden ratio and take that and its inverse, because I could have just put a minus here instead, and take that to some power 2r for an integer r. And you get this growing list of dimensions. And it turns out that for each number here, if I take this d minus 3d plus 1, the d that I get is going to be like 5 times the square, it turns out. And in that dimension, it turns out that there's a certain so that order 3 symmetry of the corner that you had before, that you're going to get something that's like in order, maybe it's not order 3r, I think it's 3. I'm trying to see if this is what I meant to say. I believe, yeah, it's order 3r symmetry group. And yeah, so we actually can say a bit more than what we said in this paper at this point. So Jean Kopp followed up with the PhD thesis that gave even a kind of a further refinement to the ansatz. But before I even tell you what that ansatz is, I need to kind of tell you a bit more background in number theory. So before I do, any questions? No? Okay. So moving on. Yeah, so maybe I'll just kind of, before I go there, so why? Why do we care so much about these number fields? Well, the hope, and not the hope, but I mean, the necessity is that, we're going to have to use that structure to prove that these exist in all the, because you can't get around it. It's like the apparent complexity of the problem in a sense. But okay, so what's an algebraic number? So, we've all had a moment in our lives when you ask Mathematica to solve you something and it spits out something like this, some kind of a root object, and you say, okay, I'll never understand this problem now. But you might look at something like this in a good way, which is to say that it's some data structure that is holding some exact representation of a number. Okay, so in particular, you can exactly tell if that number is 0 or something. So numbers like this are called algebraic numbers. So maybe to be a bit more formal, number alpha is algebraic if it's the 0 of a polynomial with integer coefficients like this. Okay, and one of the nice things about algebraic numbers is that their sums, differences, products, and division by non-zero algebraic number are all algebraic. And so not only does this let you compute with perfect precision, but there's often a lot of very interesting symmetry associated with various polynomials that you can work with, and you can try to take advantage of that when and where you can. So just for example, like the square root of -1 is an algebraic number, square root of 2 is algebraic, d of the primitive root of unity is algebraic, right? Just x to the d has to be 1. So these are called cyclotomic numbers. So that's nice. Okay, so what next? So there's a notion of a number field. So a number field is a whole collection, or it's like a vector space. It's a finite dimensional vector space of algebraic numbers. But maybe to put it in a more nice way, you could just say if I have a pile, like a list of algebraic numbers, if I just take all the polynomials in those algebraic numbers, they generate a number field. Okay, and then you're guaranteed that any arithmetic you do with those is always going to be contained in that vector space of numbers. Okay, so for example, like not just taking the square root of -1, but if you take, all such polynomials in that, you get what's called the Gaussian numbers. And you can really just think of this as some dense, collection of numbers in 2 dimensions. Similarly, you have like a real quadratic field if you don't have a square root of something negative but positive. And this is more like, it's a little harder to visualize, but you can sort of think of it as a projection of some like 2D infinite grid of numbers down to one dimension. And similarly, for like cyclotomic numbers, you just have all polynomials in that root of unity, and so on and so forth. So let's see. So I don't want to go too far into the math, but I want to just say a little bit more. So an extension of number fields mean you have you have one contained in the other. And the idea is that I can start with some number field K, and I could take polynomials, like with coefficients in K. Maybe and then you take like those for alpha, then you form some bigger field F. And we'll call such an extension normal if it's generated by all the roots of some polynomial, basically. So, or in other words, if you take the product of these guys, you get some irreducible polynomial here. And the reason we like normal extensions is because the dimension as a vector space, we call this the degree, it actually equals the order of the automorphism group, in which case we write Gal for the automorphism group to honor Galois, who died in a duel before he told us much more about Galois theory. He was like 19 or something. So yeah, so in such cases, and basically everything is normal in this talk. So I will write all my automorphism groups of fields as Galois groups. So we call an extension abelian if the Galois group is abelian, if it's Galois or normal with the Galois group abelian. And so everything I showed you so far is of such a form, right? So cyclotomic field is abelian over Q. Quadratic fields are. Just to give kind of a non-trivial example, there's this analytic function called the J invariant. It's just like, Q series. And if you plug in like an imaginary quadratic to it, you actually, surprisingly enough, get something that generates a certain class field known as the Hilbert class field. And this winds up being or I should say a certain abelian extension known as the Hilbert class field. And there's a famous theorem that's already like over 100 years old due to Kronecker and Weber, which says that any abelian extension of the rationals is just contained in some cyclotomic field. It's not super easy to prove. I mean, it is with the right machinery, but it's kind of very hard with your bare hands. But it's nice to know. But we'll just say that this is very old theorem. Like, but what you should take away from that is that just number fields whose Galois group is just abelian over Q. It means that we know how to find generators for those by taking some analytic function like this thing. The exponential series is an infinite series, but you evaluate it at these specific, like discrete points on the unit circle, and you sort of somewhat magically, I mean, maybe not so magically, but like it is sort of magic in a way that you get these algebraic numbers. And what was part of the dreams of like mathematicians 100 years ago, especially Hilbert, was that this could be generalized beyond just this abelian case over Q. And so namely, without kind of dragging this on for too long, I'll just say that like Weber back in the late 1800s, early 1900s, managed to generalize a whole bunch of this to the case where the base field Q is not, the base field is not the rationals Q, but it's some imaginary quadratic field, something like these Gaussian numbers. And again, they were trying to explain the appearance of these very intricate looking, in retrospect, algebraic numbers that were showing up in doing like certain integrals of like ellipse lengths and stuff like that, which is where like elliptic curves kind of came from. And in the process, the field of class field theory was invented as a way of mathematically arguing about fields that arise in such a way, proving that they exist, proving that they satisfy nice properties, classifying them. But the big thing that was sort of left out was how to actually generate them. Like, where do you find these things in nature? In the same way that like Weber's fields were found, or like abelian groups are named after Abel, who was studying abelian integrals, because the integrals gave you algebraic numbers that lived in abelian extensions of imaginary quadratics. So like people were looking at this stuff in the late 1800s. And to be honest, like they invented the definition of a ring to handle like the kinds of numbers that showed up in these integrals. So it's fair to say that a lot of modern mathematics was developed in order to make sense out of class field theory 100 years ago. So Taniyama Shimura by the 70s managed to come up with pretty much a complete theory for how to do this, for a huge generalization of Weber. And by saying how to do this, I mean how to find certain analytic functions that you evaluate now, not at like finite points of a circle, but you take a torus. You imagine like a 2D grid, like ZD cross ZD grid, and you evaluate certain sort of higher dimensional functions, things called things that come from abelian varieties and whatnot, and elliptic curves. They got the whole theory to work out, but when the base field is real quadratic, basically nothing's known still. Like there's conjectures, but we really don't have good ansatz yet for what the right analytic function should be, but I'll say something about this in the end. But anyway, so that's why we should be scared, okay? Because the numbers that we're seeing are not of the type that we hoped they were. And to be honest, when I first met this problem, I thought that it had to be these things that people worked out 100 years ago. It is the only reason I decided to work on it harder. But soon I realized how hard it would be. So back in 2012, Appleby, Zauner, I think this is the only other paper Zauner wrote on this. They conjectured basically that they're abelian extensions of a specific real quadratic number field. So where this number field is this thing here. So, or I should say it's real if D is greater than 3. This is actually just Q if D is 3, and it's actually imaginary quadratic if D is 2, but we'll assume D is greater than 4. So in the paper with Steve and Gary and Marcus, we actually gave an explicit ansatz for what the so there's many solutions in a given dimension, it turns out, and they all have different degrees of the number fields, and apparently there's only finitely many as far as we know, and the minimal degree extension we've realized is it's something called the Ray class field of this base field K with a certain conductor, where D prime is either D or 2D, according to whether D is even or odd. And just to give you, just for comparison, the cyclotomic field for D is the same thing over Q. So if K was Q, this field would be the D primeth cyclotomic field. So in a way, these Ray class fields are like generalizations of cyclotomic fields to higher or to like more complicated base fields. And so in Gene Kopp's PhD thesis, he pointed out that the max degree ought to be something, essentially, he said that it should be this thing called a ring Ray class field extension, which is more or less the same thing, but it kind of has, you use something different than the ring of integers. And I'll mention this on the last slide a bit. But what I will say is that these fields, like they grow with the dimension, and the degree grows like with order dimension squared. And just doing blind arithmetic in these fields can often blow up exponentially with the dimension. So things get really hard to compute as D gets large. And that's kind of part of the reason why, you know, there's always a cutoff for what dimension, because somebody's running a computer somewhere for a week to get a solution, maybe. Yeah, so just to highlight or reiterate, so Hilbert's 12th problem, which is to find an analytic way of generating these fields, find some specific functions that you evaluate that give you these kind of generators. It's still wide open for real quadratics, although there is a lot of excitement and there was possibly a claimed solution for real quadratics recently, but I'm not sure the status of that. It's certainly not accepted anywhere yet. Okay, so what about that order 3 symmetry? So I can explain this in kind of a more general setting in terms of if you take this finite Heisenberg group that I defined before and you look at, so it has a nice like automorphism group, if you consider of like projective automorphisms, where you just consider all the automorphisms that fix the center. Okay, these are the things that kind of act linearly. And so it turns out that that group always has an order 3 subgroup that stabilizes any given fiducial. And this group has a nice structure. Essentially, you can realize it as an extension like this, which kind of generalizes the other cases. And maybe I won't get too much into the details of this, but I'll just say this SL2 is like a finite matrix group. So it means I have 2 by 2 matrices over Z mod D with determinant 1. And it actually splits as a semi-direct product if 4 doesn't divide D. And otherwise, you can kind of take a quotient, but it's minor detail. And yeah, I won't say anything more about this, but maybe I'll say just the bigger the stabilizer is, it winds up, in a way we can't quite prove yet, corresponding to a lower degree number field. And also it lets you lower the dimension of the space over which you search for a solution. So it makes it easier to find solutions if the stabilizer is bigger. And in a big sense, the starting point for a lot of these investigations was this early paper by Scott and Grossel from 2009. It's a fantastic computer study where they explicitly constructed solutions in magma. And then they actually did things like calculate the the Galois group and so on. But what they did even without doing that was they listed out numerically what the size of the stabilizer group. So this stabilizer, we can call this like the group of unitary automorphisms, I guess. If you also allow complex conjugation in a given basis, I'll write the group like this. And so you allow possible anti-unitary matrices. And so they calculated the group of the anti-unitary stabilizer, the size of the anti-unitary stabilizer group in each dimension. And you see that it's almost always 3, except for when it's not, but it's always divisible by 3. And the beautiful thing is that like we can completely describe all these kind of randomly varying orders coming from the arithmetic in these number fields. So this sort of experimental data really, staring at these things and matching ansatz against it was really what helped certainly me get to my own guesses about the structure of this problem, and presumably everybody else as well. So it's the stabilizers that are giving us these random ones. So to say a bit more, so basically, well, maybe I don't think I want to get too much into this. I'll skip this. Other simplifications that may make it easier to prove that things exist, maybe would be to focus on like odd prime dimensions, and possibly even ones where the Hilbert class number is 1. And so there's a nice infinite list. And this is that record one. I think that was built right here. Presumably this list is infinite. This would follow from the Bunyakovsky conjecture. But so in other words, if you proved assuming this stuff, you wouldn't quite get an infinite list yet. And apparently nobody has managed to prove something that would imply there's infinite many primes of this form, for example, although we certainly believe it should exist. But in the last time, I want to kind of throw at you some bit more technical stuff that kind of takes us towards possibly proving existence, but I don't have too much more time, so I don't think I want to get too into it. But I just want to mention that I want to kind of tell you why these things are defined over the rational numbers. So the upshot is that there's a notion of polynomial functions on complex projective space of degree t, where what you do is you take a polynomial that has degree t and some variables z1 through zd minus, or z0 through zd minus 1, and z bar 0 through d minus 1, both the degree t in these and in these. And then you normalize by the length. So you wind up getting something that is, it doesn't depend on the length of a vector representative that you pick in projective space. And this gives me, an algebra of polynomial functions filtered by the degree t, okay? And you can also break this up as a direct sum over harmonic polynomials, where you call a polynomial harmonic if it's in the kernel of this Laplacian operator, okay? So it's not hard to show that some set of unit vectors forms a t-design if and only if these are the common zeros of all the harmonic polynomials up to a given degree, okay? And to say a bit more, if I have a group that's acting, then the orbit of a group is a t-design if and only if, like, my vector is a common zero of all the invariant harmonic polynomials up to degree t. And this is something really Sobolev looked at really like a long time ago in the 60s for like platonic groups acting on the sphere. He proved some nice theorems. And so from this, we can kind of get a nice corollary that, a fiducial vector is one if and only if it's a common zero of all just the degree 2 harmonic polynomial functions that are invariant. Because the degree 1 ones there's no harmonic invariance in degree 1. And actually, we even have some nice dimension formulas here. And you'll notice that these almost look like my magical number, but it's like the opposite. So plus and minus get switched. And I can maybe say something about that in the end. But okay, so there's what you might call a graded Q-algebra. So a graded algebra. So it's just some ring that has a copy of the rational numbers in it. And what a grading means is that it's split into subspaces such that, like, Rn times Rm is contained in Rn plus m. And what this ring is, you just take like all the degree n comma n polynomials in the z's and the z bars to look like this. And then if you just form these harmonic subspaces, which are the kernels in these polynomials, they restrict to polynomial functions. So Like here I was talking about like literal functions on projective space, whereas here I'm talking about polynomials that you get a function by evaluating it at some point, okay? And so the degree n part of this ring breaks up into a bunch of harmonic subspaces where you pull out powers of the length, essentially, okay? And that's why you have this filtration, basically. And so maybe this is more technical than I wanted to get into, but the upshot is that I want to then look at the invariant ring under the ZD cross ZD action by the generalized Paulis. Okay, so maybe this is a bit more technical. I'll just jump to the next page, and I'll just say that if we take a function, or one of these polynomials, and you average over, the Pauli group, the generalized Pauli group, you project it down to the invariant subring. Okay. And so this invariant subring then maps into a space of invariant polynomial functions, which you can also look at as polynomial functions on the quotient of the projective space mod this finite group. Okay, so in other words, the space of orbits, the space of ZD cross ZD orbits. The reason I like this space is that these are all, a point in this space, something that might be a SIC-POVM. You want to know which points have equiangular orbits. And so one reason we jumped through all these hoops is that this ring of functions is rational. Okay, it just has a rational basis. Okay, and so then it turns out that we can actually get a nice basis for the space of degree 2 harmonic invariants. They're actually spanned by these very specific polynomials, where really I'm just taking these degree 2 part and I'm pulling out the right kind of scalar part of the length. Okay, and then if you take into account some simple identities obeyed by these things, you have an explicit dimension for this vector space of polynomial invariants. So in other words, you want to know if a vector is a fiducial, you have to check exactly this many polynomials if the dimension is D, or if the dimension is odd or even, and they're easy to find. Okay, so I don't know if I said this earlier, but it's apparent that the solutions are isolated. Okay, which can be formalized by the notion that these equations cut out what's known as a zero-dimensional variety or zero-dimensional projective scheme, to use some precise language, which I guess I'm kind of in a borrowed time here, so I can just blast through this. So the upshot is that it's not terribly hard, or this is in progress, but I think that it's not far off from being able to prove that basically that the set of all what I might call potential fiducials is non-empty, because apparently it's zero-dimensional. But the hard part is basically not so much proving that you have a solution to these equations, right? But so proving that those equations have a solution is equivalent to kind of what I've shown down here at the bottom. So there's some specific ideal in that ring, and I need to show that its saturation does not equal what's called the irrelevant ideal. And this is the thing that keeps everything in all degrees except for degree 0. But one has to show a bit more. Namely, you have to show that you get something that kind of that plays right with the complex conjugation. And so there's a notion in commutative algebra, something called a field value point, where for the sake of this talk, I could say it basically corresponds to like a homomorphism from the coordinate ring for an affine coordinate ring into a field. That takes a homogeneous polynomial, in this case, one the same degree in z's and z bars, to a scalar. And really, this is a very complicated way of saying I plug in some vector v here and its complex conjugate here. Okay, but the upside is that this ring carries some natural involution, like just takes, we'll call it bar, and it just swaps the z's and the z bars. And so here's a theorem that there exists a fiducial if and only if there's a complex field in an f value point, which would be a solution mod this complex thing, but such that if I act with the involution, I get the complex conjugation in the field in which it's valued. Okay, so there's a lot of subtleties here in the sense that this complex conjugation has to actually be an element of the Galois group of this field. Okay, and maybe just to say, I think this is the last of the fire hose here. Okay, so something the Zariski closed points of this scheme. I mean, this is some topological space And what's known as the closed points in this space are, these are the ones whose minimal field of definition has a finite degree, i.e. it's just a number field. Okay, and we believe that in dimensions not 3, that they're all zero-dimensional. And it's known that there's a bijection between the zero-dimensional closed points and the Galois orbits of just the ordinary solutions, okay? So the upshot is that because this thing has a non-abelian Galois group, anything that doesn't commute with complex conjugation basically spoils the complex structure. But Gal F over K is abelian, and all that does commute with C. So kind of piling all that together and taking in what we know to be true but haven't proved yet is the reason I wrote this in red. So we can conclude that the actual fiducials should form some kind of a projective scheme defined over this base field alone. But I can't quite tell you how to construct them, but I can do it on a computer, but I don't have an ansatz yet for like how to find nice equations. Maybe to just leave it with one more kind of different direction. So one famous approach to Hilbert's 12th for real quadratics and more generally is something called the Stark conjecture, which back in the 70s, Harold Stark realized that essentially a certain generalization of the Riemann zeta function, something called like an L function in number theory, should, if you take like certain derivatives at 0 and evaluate them in the right way, you ought to get algebraic numbers that generate all the class fields of that field. Still just a conjecture, but maybe this may change very soon, I'm not sure. There's an interesting reformulation, or I should say co-discovery of these conjectures by Shintani in Japan. And he formulated very similar equations, which I guess he didn't know about Stark's work at the time, in terms of a kind of an ancient almost analytic function known as the Barnes double gamma function, which is this guy here, where you take this double zeta function where you're summing over n1 and n2 greater than or equal to 0, depends on some parameters epsilons, and then you take an exponential of the derivative at 0, and you get something that like diverges, and you need to use some sort of regularization technique to extract numbers from this that's entirely similar to things people do in quantum field theory. And the truly remarkable thing is that Shintani's work is mostly cited not so much in number theory, but actually in quantum field theory, where his transformation formulas were used in the study of something called Louisville theory, which is basically a theory of like two-dimensional critical string theory that gives kind of a recently proved construction of quantum gravity in 2 dimensions. And so the upshot is that like there's a bunch of parameters that show up in the physics, and there's something called the background charge, which if you set that equal to the dimension -1, there's these other numbers B and B inverse that kind of play a specific role in governing the physics. And I'll mention that like B plus -1 is given by this quantity here, which shows up in this ring that I mentioned earlier on that Kopp wrote down in his generalization to the ring ray class fields. So I think getting to the bottom of this might really reveal some shocking new connections with physics, and that's very much underway right now. But I think I've used more than my remaining time. So let me just thank everybody for coming and hanging out on a Friday in the middle of the summer, and just conclude by saying that like it may be the case that somehow for Hilbert's 12th that possibly what was overlooked is to look at multivariate polynomials and not just single variate polynomials. And it seems that kind of the indefinite nature of like the quadratic forms that are relevant for this problem may be better handled in that kind of a setting. I have many other conjectural approaches to this problem, which maybe may shed light or may get light shed on them once we understand things. One is that I conjecture that these configures may correspond to some sort of like optimal harmonic tori embedded in projective spaces. There's also some very interesting connections to minimal triangulations of the complex projective plane, at least, which will have to be for another talk, another day. So thanks a lot for listening.
Thank you, John, for the nice talk. So you have any question for John, please unmute yourself and ask the question.
I have a question. So has anybody looked at this problem as something like an optimization problem over a space of all possible lines? And what types of results can you get sort of looking from that perspective?
Well, in a sense, I mean, if we're just, one can write down a single polynomial.
Yeah.
That that it's minimized, it gives you a fiducial vector. And people certainly just do like gradient descent, they always find them. But proving that that works, I think people have tried. I know Vern Paulson had some attempt to show that like if he could kind of go towards a solution and if you could get close, maybe that would work. But it seems that any attempts people made, like Cohn, Kumar, Minton, they did something. They had these effective existence theorems for the real quadratic case, or for the real equiangular lines, where they could show if they get within epsilon, they get all the way there. But of course, it breaks down for the complex case. And
why is that obvious?
Well, because the problem's hard. I mean, like, I'm not saying it's obvious at will. It's just that you expect that anything that is going to try to be a hammer of Thor, and this is just not going to work. But I mean, what I'm able to do is I'm able to like just feed my pile of equations to like magma and say like, list the points in this scheme, and it just does it. Mm. Well, this is partly why I gave up on magma, because it doesn't do it too well, because like the complexity of like the Grosvenor basis algorithms scales like exponentially with the number of solutions. And that's part of the reason why like it's nice to actually mod out by as much symmetry as you could hope to do. So I was able to actually compute some decent solutions using magma, but the closed sourceness of it made me basically give up. And so I'm kind of in the middle of doing this with some better packages where I can actually look under the hood, like Oscar using Julia is what I've been kind of heavily working with. And I was hoping I'd have more specifics to say, but that'll probably be for a next talk.
Thank you. Other questions?
I'd have a beer with you guys, but it's only 1:30 here.
Okay, if not, let's unmute ourselves and I give applause to thank John.
Yeah, thank you.
Okay, let me stop recording and